Let's start by introducing the web platform. Okay, so now we're jumping into the real side of the story, and I'm going to provide you with a primer on how the web works, which is important to understand how web vulnerabilities arise. First of all, let's clarify the scope of this course. The web is a very broad concept. Okay, when we discuss about web security, we might mean different things. We might mean, for example, the web infrastructure security, including, for example, the DNS systems, the internet, and other issues, for example, security of email providers. In this course, we are concerned about one specific aspect of web security, which is web application security. That is, security of applications which are developed to run over the web. So if you are a programmer and you write distributed application, you're probably to get the most out of this course. What is a web application? Is a distributed application, so an application running with multiple components on different hosts, and they're implemented normally following the client-server model. So we have some component which sends requests, and some other component, the server, which processes the request and provides the response. Web applications are normally operated by a web browser, meaning that normally the web browser is the client, but you are familiar now that many web applications are actually accessed through mobile applications. For example, if you have a Facebook account or an Instagram account or whatever other social network account, you can access that using a web browser, or most commonly, you can access that using your phone, using an Android application or an iOS application. So the client might change, might be a traditional browser or a mobile app. We're not going to cover a mobile app in this course, but we have a client component, which interacts with some server component, which is somewhere else on the earth. Web applications are very popular. I provide you some examples of very famous services with important security requirements. I'm pretty sure that everybody in this room already interacted with some of these applications, or maybe most of them. For example, I think that all of you bought something from e-commerce websites. I provide here different examples from different geographic area. If you are from Asia, probably you buy something from Alibaba. If you are from Europe or US, most probably you bought something over Amazon or eBay. For sure, you all have mail accounts. Back in the days, mail accounts used to be operated using a mail client like Thunderbird. They're still around, but nowadays, most people access their email using web applications, such as the Gmail web application, but Outlook and Yahoo also have similar services. And finally, we have social networks, other example of prominent web application, such as Facebook, Instagram, Twitter. We use them on a daily basis, but the key problem is that they're very hard to protect. So ensuring the security of services like this one is very complicated, and major players here have teams of security engineers who are in charge of raising the level of security of their web applications. What are the challenges? So why is it so difficult to protect web applications? There are multiple reasons. I give you in this slide the 3 reasons that I think are particularly important. One of the reasons is the value of web assets. For example, assume that somebody is going to steal my Google password and access my Google account. They can access my Google Drive, and my Google Drive contains tons of content which is related to my job activity. So if somebody is going to steal my Google credential, they can access confidential information. If somebody manages to enter in my Amazon account, they can buy stuff using my own credit card. So there are tons of sensitive data and security sensitive functionality which are enabled by access to a given online account. So the more the web integrates with everyday life, so the more the web becomes part of our physical identity, the more web assets are valuable, and the more attackers are encouraged to try to get an advantage from some vulnerability. So the more value you have, the more you might become a target of attackers. So services like Google, for example, or Dropbox, need to be really safeguarded against attacks because they have so many users and they store so much valuable information that they're primary targets. That means that all the best hackers in the world will try to enter into these systems. The second reason why web security can be challenging is that the web is open-ended in nature. That means if you write a web application, you want as many people as possible to access the web application. Okay, so web applications are publicly accessible by design. Everybody on the internet can try to register to your web application, log in, interact, whatever. So everybody in the internet can act as the attacker. So you have a lot of value, many people who can try to get the value, which is a very challenging scenario. And the picture is complicated by the web complexity. If you want to be an expert about web security, you must first be an expert about web technologies. It is clear that we won't have time in this course to become experts about any web technologies. So I will try to keep this course somewhat unrelated from technology, in particular from specific details of programming languages. But there are many different technologies involved in any real web scenario. You have a browser, which executes some JavaScript code, and the page interacts with some server-side component, which can be developed using tons of different programming languages that talk to some database to retrieve data, and the communication happens over an untrusted network. So there is also a communication component. Most importantly, many web technologies are, for example, scripting languages. Scripting languages have some unconventional semantics, many quirks, and whenever you have quirks, you might have vulnerabilities. So in general, it's a challenging topic because you need to master different technologies, and not all of these technologies are developed to be security savvy. So it's going to be challenging. Let's introduce the first of the technology we must know to reason about web application security. The first ingredient I want to introduce you is the HTTP protocol. HTTP is a short for Hypertext Transfer Protocol. It is what I call the workhorse protocol of the web. So every web application runs on top of HTTP, or its encrypted variant, which is HTTPS, which we're going to discuss. What is HTTP? Of course, it's a real-world protocol. Real-world protocols can be complex, but we can summarize the key ingredients of HTTP in terms of just a few bullet points. It is a request-response protocol based on the client-server model. You can see an example here. You have a client, most normally a web browser. You have a server, which sits somewhere else in the internet. The client sends a request. The server processes that. After a while, it provides back a response. So communication is asymmetric. We have requests and responses with different shape and formats. This is something that we're going to discuss soon. Other important ingredients from a technical perspective, HTTP is plain text. So it's a protocol which has no security guarantees built in, which means you have no confidentiality of the message. Everything which flows through the network using HTTP can be read by anyone sitting on the network. So if it passes through multiple network hops, the hops will see the content of the message. You also have no integrity. That means the attacker can modify messages in transit. So everything which is sent over the network, if it is sent using the HTTP protocol, can be modified. You have no integrity guarantees. And finally, you have no authenticity guarantees. So when you communicate with some host, you have no guarantees about its identity. Okay? Of course, this is a nightmare from a security perspective. We have ways to solve that using HTTPS, but in its definition, HTTP has no built-in security guarantees. The last component which is important to understand, because it has relevant security implication, is that HTTP is what is called a stateless protocol, which means that the server has no memory. When you send some HTTP request to the server will treat that as an independent event. So the server doesn't save any state which is preserved through multiple HTTP requests. Meaning that if you want to build a stateful application, you must do that at the web application layer. We're going to discuss this by the end of this class. How can you access something using HTTP? You are familiar probably with the concept of URL. What is a URL? It's a uniform resource locator. So it's a way to refer to some resource which is hosted somewhere on the internet. You're already familiar with simple URL, for example, www.facebook.com. However, URL syntax can be complicated. So you can find here what is the syntax of a URL, where I use the square brackets to denote optional components. So a URL for sure must contain a scheme, and the scheme is a protocol. In the context of web security, the protocol is normally HTTP or HTTPS. We have a host, and the host is essentially the server, which contains the resource you want to access. And you have a path, which identifies the specific resource on the server. So scheme tells you how you want to access a resource, so be that HTTP or HTTPS. Host identifies the remote server. The server is identified either using an IP address, which identifies a specific machine, or most commonly using a mnemonic name, which is called a domain name, such as google.com, unive.it, whatever. So we're going to talk about the domain system in a moment. And the path, similar to what happens on the file system, is a /separated string which identifies one specific resource on the server. However, as I mentioned, the syntax of URLs can be complicated and include additional components. One component probably you're not familiar with are the authentication credentials. So in the URL, you can prepend, using the @ symbol, some username and password pair. For example, Alice:secret means I'm user Alice and the password is secret. So you can exchange credentials using HTTP, using a mechanism which is called basic authentication, which is basically not used in modern web application, but it's part of the syntax of URLs. Another component which might enter URLs is the port. The port is normally omitted because protocols have default ports. For example, 80 is the port for the HTTP protocol, and 443 is the port for the HTTPS protocol. But you can specify a port, if needed, using the colon. Other relevant parts of the URL include the query string and the fragment identifier. The query string, probably you already seen that. you might have realized that in some URLs, you find a question mark. And whatever is put after the question mark are essentially additional parameters of an HTTP request that you're going to send. Parameters are normally separated using an ampersand, but this is not part of the standard. It's a kind of a standard de facto, but you can put whatever you like into the query string. The most common syntax is parameter 1 equal to value 1, ampersand, parameter 2 equal to value 2, etc. As many parameters as you like. The fragment identifier, instead, is the part after the hash symbol. It normally identifies some part of the HTML page, which is called an anchor. So for example, if you have a very long HTML page, you can create multiple anchors so that users might click over a link and jump to the specific part of the very long page that you created. The fragment identifier is never sent to the server. So it is part of the URL syntax, but it is the only part of the URL which essentially is not communicated to the server when you try to access that. It never leaves the client. This is going to be useful in some web protocols like OAuth, because somebody tries to sneak in here some confidential information which should never leave the client. Let me discuss an interesting aspect about URLs. As I said, first interesting aspect is the syntax is more complicated than what you would expect, and we're going to discuss abuses which leverage exactly the complexity of URL parsing. Another aspect which is interesting to learn is URL encoding. What is URL encoding? It's a technique to translate characters into a format which is amenable for representation as a URL. The URLs are built on top of the ASCII alphabet. Okay? So the ASCII alphabet is essentially the standard alphabet for Western people. But there are tons of characters which are not part of the ASCII alphabet. For example, if you write in Chinese, if you write in Arabic, if you write using some other characters which are not, let's say, so common that you can find, for example, on a traditional English keyboard. So since the URL is built on top of the ASCII alphabet, but you may want to create URLs containing non-ASCII alphabet, you have a way to encode non-ASCII characters in the ASCII alphabet. That's the encoding procedure. So it's a translation from, let's say, non-ASCII character into ASCII characters. Okay? That's what is called URL encoding. So that's the main purpose, but you also have other purposes for URL encoding, which is to give a literal meaning to some reserved characters. So what is a reserved character? It's a character with a special meaning in the syntax of URLs. For example, we said that the slash is the separator of the path component. The question mark is the separator used to denote the query string. So if you ever want to use these symbols with their literal meaning, so as characters with no specific semantics, you can do that using the URL encoding. This concept is going to be intuitively clear for you, for example, if you use Linux. Because when you work with a terminal in Linux, you are similarly forced to encode or escape some special characters. For example, let me give you this example. Let's assume we are on a terminal, and we want to create a file containing a whitespace character. So, for example, we can use the touch command to create a new file. So with touch, you create a file with the given name. So let's say I write touch AB, and then I ls afterwards. You will see that I have created two files in this folder, the file A and the file B. That's because the whitespace has a special meaning to the Linux shell, which is a separator of parameters. So in this case, I created one file which is called A, and one file which is called B. So if I want to create a file which is called a white space b, I have to tell to the shell that I want to encode the white space and give it the literal meaning. So if I want to create a file which contains the white space, I have to escape that using a backslash. As you can see here, I finally created another file, which is represented like this, which has exactly the white space within the name of the file. So the concept of escaping or encoding is common in computer science, and you probably have done that before. In the URL parlance, that's exactly the same story. Some character, like the white space for the shell, have a special meaning, and if you want to use that with the literal meaning, you must encode that. So what are the rules? Of course, if you encode a reserved character, you modify the meaning of the URL. If you put the encoding of a question mark, you are not denoting a query string. If you don't encode that, you are starting the query string component. While URLs which differ, because you encode some non-special character, like the big A, they have no special meaning. So an encoded character and a decoded character are the same if the character is unreserved. This notion can be complicated because the concept of reserved characters depend on the context. For example, the slash is reserved when you use that in the path, because in the path it is the standard path separator. But if you use the slash in the query string, encoding might not be necessary. Here we see an example of a URL encoding of a string. These strings contain some characters which cannot be used in the syntax of URL. The characters are the white space and the slash. And if you encode that, you will see this representation. So the white space is represented by this triplet of ASCII character, %20, and the slash is represented by this other triplet, %2f. Okay, so this is the encoding using the URL encoding scheme. And if you ever see something with the % symbol within a URL, it's URL encoded. Let's see some examples. So in this table, I propose you with pairs of URLs. And the question is whether the URLs which are presented in this slide are valid. So URLs can be invalid if they do not comply with the URL syntax. And whether they're pairwise equivalent. So if the two URLs in the same row are equivalent to each other. Let's check the first two URLs. What is the difference between these two URLs? The difference is that the small c character in here is URL encoded. Okay? So the small c is translated as %63. So what do you think? Are these two URLs equivalent or not? Let's make a poll. How many will say they're equivalent? Raise your hand. 1, 2, 3, 4, 5, 6, 7, 8. Okay. How many of you think they're not equivalent? 1, 2, 3, 4, 5, 6. Okay, so it's half and a half. They are equivalent. And the reason why they're equivalent is because the small c is an unreserved character. So it's unreserved. It has no special meaning. Okay. So as I said in the previous slide, URLs differing only by whether some unreserved character like big A is URL encoded or not are equivalent. So if you just URL encoded some character which does not need any encoding because C has no special semantics, it's part of the ASCII alphabet, don't need to encode it. If you encode it, it doesn't change the meaning. So the first two are equivalent. Let's check the other two. So on the left, we have this URL, the same as before. On the right, we have this other URL where the slash character is URL encoded as %2f. Do you think that these are equivalent or not? These are not equivalent, and the reason, as we said, is that the slash has a special meaning. So if you URL encode the slash, you're telling, I want to use slash with its literal meaning, like this symbol, and not with its special meaning. The interesting news is that this URL here is not valid. And the reason that it is not valid is that if you check this, technically speaking, the % symbol will be part of the name of the domain. This is forbidden. You cannot register a domain name including a % symbol. So these are not equivalent, and the right one is not even a valid URL. If you try to parse that, you get a parsing error. Finally, let's check together these last two examples. So here we have this URL, and here we have a variant of the same URL where the hash symbol is encoded as %23. Are they equivalent or not? They are not equivalent because the hash has a special meaning. It denotes the fragment identifier. If you encode that, you will tell to the browser, this is not the fragment identifier, it's actually the hash symbol with its literal meaning. If you're confused about that, you can play with the browser console, the JavaScript console in particular, to understand what's going on. Let me show you how it works. So assume we have a web browser open. This is Chrome. If you're using any browser, you can open a JavaScript console. So the JavaScript console allows you to execute JavaScript code. So JavaScript, we're going to mention, is a programming language which is executed directly into the browser. And what is interesting is that you can use the URL class of JavaScript to see how the browser interprets a given URL. Let's try together. Let's consider this URL here. With this line of code, I'm creating a URL object starting from the string that I provide. So if I execute this code, you will see that JavaScript creates a JavaScript object which contains a lot of information about how the browser interpreted this URL. So in this case, you can see that this object has a property which is called hash, which contains the fragment identifier. So in this case, the fragment identifier contains hash C. The host, which is the domain name roughly, is a.com. There is no password. There is basically no path. The protocol is HTTP. And the query string, which is found in the search property, is $B. So this is the interpretation that the browser gives to this URL. So it's some URL with the HTTP protocol. You can find that in the protocol property. The domain name is a.com. We have a query string which is $B and a fragment identifier which is hash C. So that's how the browser parses the URL. If we rather try the companion URL, so the one which we said is not equivalent, let me try. Let's see what happens. as you can see from the created object, you will realize that the interpretation of this URL is completely different. And the reason is that, for example, the hash, so the fragment identifier of this second URL is empty, while the query string component, which you can find in the search property, is much larger. Because in this case, what we are telling to the browser essentially is this string here if we interpret this as a literal, is just a query string containing this free character. While if we give to this character the special meaning, we are saying that this is the query string, while this is the fragment identifier. So URL encoding plays a major role when you reason about the semantics of URL. If you are curious about URL parsing, you can use the URL class of JavaScript to create appropriate objects which tell you how the browser interprets that URL. Some other technical content in this slide, if you want to play with URL encoding. These are the JavaScript functions to perform URL encoding and decoding. So if you want to see how URL encoding and decoding works, you can use encode URI component and decode URI component. And if you want to reason whether two URLs are equivalent, you can think about the following algorithm. So you first parse the URL. So you basically build the URL object that we described in the JavaScript console. And after parsing, you compare the decoded URL component. In terms of code, that's a simple way to compare two URL in JavaScript and determine whether they're equivalent or not. So as you can see, this function takes as input two URLs, UR1, UR2. It performs parsing by creating URL objects as we discussed in the previous slide. And afterwards, all the components of the parsed URLs are compared after performing the decoding. This exception here is useful to catch the cases where one of the URLs is not valid. So we mentioned invalid URLs. We can see how the browsers behave with invalid URLs. Let me show you. Let's pick this URL here, which we said is not valid. If we try to parse that, you're going to get an exception. It's down here. Uncode type error, failed to construct URL, invalid URL. So this is not good because it tries to build a URL including a slash within the domain component. This is forbidden by the syntax of domain. Okay. So this is a good, let's say, way to understand how URL encoding and URL comparison works. Be aware that subtle cases might still occur. So this is the best approximation I came up with for this class. Let's discuss now domain names. So we referred multiple times to domain names. You already have familiarity with domain names, which are the mnemonic name used to identify websites. Let's introduce some terminology though, because this is going to be important. So on the web, we normally identify a server using a string, which is called a fully qualified domain name, FQDN for short. So an example of fully qualified domain name is www.wikipedia.org. Okay? It includes basically the full identity of the server in a sense. Okay? So this identifies the machine that you want to communicate with. Wikipedia.org is called a domain name, or domain for short. So this is what you can register. So we're going to discuss about the domain registration in a moment. So you can buy, for example, wikipedia.org, unless somebody else already bought that. And after you buy that domain, you can host multiple subdomains under that. So for example, dub.dub is a subdomain of the domain wikipedia.org. So you can think of domains and subdomains like a tree. So org is the root of the tree. After that, you have wikipedia.org, and you have another subdomain, which is dub.dub. So you can buy a domain like this and host different subdomains under that. And the org component is called a top-level domain. You have tons of different top-level domains like com, IT, whatever. There is a protocol which is called DNS, the domain name system, which is in charge of translating this human-readable representation, the domain name, into an IP address. So into an internet address which identifies a single host. How does it work? We can see an example in this slide. The process is recursive. So you have a component which is called the DNS iterator, which is in charge of resolving domain names into IP addresses. So the DNS iterator knows the IP address of what is called a root name server, like 198.41.0.4. So whenever you want to learn what is the IP address of www.wikipedia.org, you try to contact the root name server. And you ask about the corresponding IP address. In this case, the root name server doesn't know how to resolve this name, but can delegate that to another name server. So the root name server can say, try some other different IP address. So the DNS iterator operates recursively and will ask the query to another name server. As you can see, this name server is in charge of resolving everything which is under the org top-level domain. It is plausible that also this name server doesn't know the answer to this query, but can redirect again our DNS iterator to the next name server which is in charge. Notice that the IP address supplied in the response here is exactly the IP address of the next name server. The next name server is in charge of resolving wikipedia.org. So the name server here finally knows the answer. So this name server here knows exactly the IP address which is associated to www.wikipedia.org. So here, with the last response, DNS resolution stops, and now you know the IP address that you can contact. A few notes on this slide. First of all, terminology. A domain which is associated to at least one IP address is called a host name. So it's a name for a specific host, for a specific machine. And the mapping between domain names and IP addresses, using the database terminology, is a many-to-many mapping. Why is it many-to-many? So let's reason together. Why is it common, for example, for one domain name to be associated to multiple IP addresses? So why do we think it's useful? Redundancy, so for fault tolerance. So it might be that some machine is unavailable, or for balancing the load. Load balancing can also be an option. So the intuition that one domain can map to multiple servers, it's reasonable. What might be a little bit more obscure is how is it possible that one single IP address is associated to multiple domains? Any idea about real-world scenario where a single IP address is actually in charge of serving multiple domain names, there is a very simple use case, which is virtual hosting. So if you buy some machine, say on Aruba, Aruba is not going to give you one physical machine. The machine is shared with other people who buy domain on Aruba, and all the requests will be sent to the same IP address, so the same physical machine. And the same physical machine uses a specific header, which is called the host header, that we're going to introduce, to determine for which domain the request has been sent. Of course, the process of DNS resolution can be costly. As you can see, it's a recursive process, which might require multiple hops, which means that normally DNS resolution is cached. So it has some time to live, some duration, and the output of DNS resolution stays in the cache. Domains, as anticipated, must be registered. So if you want to use a domain, you have to pay for that. The price depends on the name of the domain, on the top-level domain, on the registrar, which is the entity in charge of performing domain registration. So you have to pay a fee. You have multiple services. Here I mentioned Aruba or GoDaddy without any advertisement purposes. I have no interest in these services, just to provide an example of popular ones. So if you want to buy a domain, you go to the web interface and you register the domain. How is a domain defined? This is an interesting terminology you might not be very familiar with. A domain is one label, which is the name of the domain, say Facebook, followed by what is called a public suffix. So what is a public suffix? Is similar, but not exactly the same as a top-level domain. Why is not exactly the same? Let me give you an example. If you think about UK websites, up to a few years ago, you could not register any domain under .uk. Now you can, but up to 2014, if you wanted to host some website based in UK, you were forced to register that over co.uk. So you could not place any domain such as bbc.uk, but you could register bbc.co.uk. So the public suffix is exactly the rightmost part of the domain name. So it's the part of the domain name on the rightmost component which is associated to registrable domain. So technically speaking, in this context, UK is the top-level domain because it's the one which is most on the right, while co.uk is the public suffix. So any registrable domain must terminate with that. Okay. Registrable domain are also called sites in browser security. So it's a kind of recent terminology, but when you hear about sites, you mean exactly the registrable part of the domain. So for example, bbc.co.uk is a registrable domain or site. The list of public suffix is available online, so you can check it there. As I mentioned, you can think of domains like a tree structure. So whenever you buy some registrable domain, such as bbc.co.uk, you can create as many subdomains as you like and control DNS resolution. So you can, for example, make different subdomains resolve to different IP addresses, so to different physical machines. And here you can find an example. If you buy bbc.co.uk, you can create subdomains such as foo.bbc.co.uk and bar.bbc.co.uk. And you have full control of the DNS records. So you can make these different subdomains resolve to different machines. As the owner of the registrable domain, you are the one who is in charge of creating subdomains. So no one else can create subdomains for bbc.co.uk except for the site owner. let's start now discussing HTTP requests. As we said, HTTP follows the client-server model. So the client sends requests, the server sends back responses. The structure of a request is shown in this slide. So the request starts with what is called a request line. The request line has a kind of a fixed structure. It includes a method or verb. The method in this case is post. It's the first keyword included in the request line. So this is from a fixed vocabulary. So you have just some methods that we are going to review: get, post, options. So you have several methods, but these are taken from a fixed vocabulary. So that's the method. That's the resource that you want to access, for example, /cart/add.php. And this is the protocol version, HTTP 101, which is the standard one right nowadays. Then you have a line break. The line break is actually a pair of characters, carriage return line feed. And after that, we start enumerating request headers. Headers have also a fixed structure. So they have the name of the header and the value of the header with a colon as a separator. So here we provide an example of the host header that we mentioned, where the value is www.amazon.com. So this includes the domain to which the request was sent. This is useful, for example, for the virtual hosting cases that we mentioned. You can put as many headers as you like, separated by line breaks, until you put an empty line. That's the separator between the header part and the body part. So after this empty line, you can put, optionally, a request body. So whatever content you want to communicate with the server, which doesn't fit the header. So in this case, we are telling to the server, we want to add to the cart some item with this ID, and just one component suffices. Okay? What are the possible methods? In this slide, I show you the most common ones. Get is a very popular one. It's essentially read. So with the get method, you can retrieve information from the server. Post is the write operation instead. With post, you send the data to the server with the goal of letting the server process that. In the previous example, we wanted to put an item into the shopping cart. That's most naturally a post. So you're modifying the state of the server. The head method is similar to get, so that's read, but it does not download the response body. So you're just asking the response headers. Okay, that's why it's called head. Other methods which are famous are put and delete. This deals with file upload. With put, you can upload some file on the server. And with delete, you can essentially delete files from the server. And finally, the option method is a way to interrogate the server and ask for which are the supported methods. Because web applications do not necessarily need to be able to support all these methods. They might support just a subset, and with the option method, you can query for the supported method. If you check the HTTP spec, you can build a table similar to this. So for the different methods, you can find whether we have a request body and a response body. For example, in the case of GET request, the body is optional in the request, but mandatory in the response. So you can find this information in the HTTP spec. And moreover, you will see, most interesting, that methods are classified as safe and idempotent. What does it mean? Safe means the server state does not change. So if you think about the semantics that we discussed, the get method is safe because it reads from the server. So it is not supposed to modify the state of the server. and similarly for the head method. While methods like post, put, and delete, for sure, were not safe. Because in one case, you upload a file, in one case, you delete a file, and in another case, you ask the server to process data. For example, add something to the shopping cart. So these are not safe. Idempotency means executing the action multiple times is equivalent to executing that just once. For example, if you read, the read is for sure idempotent. So if you read multiple times the same resource, you always get the same content. Put is also idempotent. Uploading a file once or twice doesn't change. Similar for delete. Deleting a file once or twice doesn't change. The file is deleted. An example of a method which is not idempotent is post. Adding an item to the shopping cart once or twice might make a difference. Also for idempotency, there is no guarantee that developers are going to comply with that. So please be aware of this when you develop your own web application, but also please be aware that developers might not comply with this table when they develop the application that you want to target. We discussed requests, now let's discuss responses. So what is the structure of an HTTP response? The first line is special again. It's called a status line. In the status line, we include what is called a status code. In this case, it's 200. Status codes are again from a fixed vocabulary. So you have a list of known status codes. In this case, it's 200. And the reason message is OK, which means this request was processed correctly, and this is the corresponding response. So status line is the special line at the beginning. After the line break, you start with response headers. Here, I provide just one header, but you can provide multiple headers using multiple line breaks. Here, we use the content type header to tell to the browser that this is an HTML document. Okay? After all the headers, you put an empty line, which acts as a separator, and after that, you are free to go with the response body. So in this case, we have a tiny one-line HTML document, which just includes the string done. Okay? Status codes are plenty. I don't know the exact number, but there are many status codes. What is interesting to remember is that they are divided in categories, where the first digit of the status code gives you the category. So if the status code starts with 2, that's success. So the server processed the corresponding request correctly. An example is 200 OK. We already mentioned that. Status code starting with 4 mean a client error. For example, 401 means this client is unauthorized. So there is a resource here. Somebody is allowed to access that, but this client is not allowed. Can you tell me another famous status code which starts with 4? 404, not found. That's the client fault. Okay? The client requested something which is not on the server, so it's the client fault. That's why it starts with 4. 5, status code starting with 5 are server errors. For example, service unavailable suggests that probably the server is overloaded. So when you get an error starting with 5, do not start hitting F5 as crazy, which is what I usually do, because it might mean that the server is overloaded, and if you overload it further, it's not good. So it means the server cannot answer at the moment. So the request was fine, potentially, but the server is dead or has some problem, and you are not able to access that. Again, let me stress that this is a convention. You can provide an error page with the 200 status code, but this is not what you are supposed to do. So developers can ignore this, but this is the convention. What is important to note is that we have one special category of status codes which have a clear semantics, and are the status codes starting with 3. These are redirects. So if the page sends back a response with status code starting with 3, this is telling to the browser that the browser should request from a new location. So there is a special response header which is called location, which tells to the browser, move somewhere else. For example, because the page used to be there, but you want to move it somewhere else. So these are the only cases of a status code with a well-defined semantics. So the browser, if it receives some status code starting with 3, will always follow with a new request to the content of the location header. Response body, that's text. Okay, so you can put whatever you like into the response body, but some text has special meaning. So what is most prominent to know when you reason about web application? HTML, so the hypertext markup language. I don't know if you're familiar with HTML. It's actually pretty straightforward. It's a way to define the structure of a web page. So basically you use tags to define the structure of the page, and these tags get parsed to produce what is called a DOM tree. So the DOM tree is a tree-like representation of the HTML document. We're going to discuss that in the next lecture. And the browser builds the DOM tree before rendering, and the HTML document is formatted for presentation using another standard which is called Cascading Style Sheet, CSS. We're not going to cover CSS much in detail in this course, but it's just a way basically to tell this should be bold, this should be red, this should be hidden, so you can customize the appearance of the web page rather than the structure of the web page. So HTML defines the structures, CSS defines the presentation, essentially. Another important technology that I want to mention that we're going to investigate a little bit more in depth during the next class is JavaScript. JavaScript is a full-fledged programming language. You can write arbitrary applications using JavaScript, and now JavaScript is used in many different contexts. But in its original formulation, JavaScript is intended to run on the client side. So that means that the browser integrates a JavaScript engine and executes JavaScript code as part of the rendering of the HTML document. Nowadays, it is used basically on every website. When I started using web browsers, which was like 98, 99, you could disable JavaScript. And some sites didn't use JavaScript. Nowadays, if you disable JavaScript, you will break every website. You're basically unable to interact. What is interesting about JavaScript, it has actually many interesting and not so interesting features, but what I want to mention is that it has access to powerful APIs. So since it integrates within the browser, for example, it can manipulate the DOM. So it can modify the structure of the tree-like representation of the HTML document. So it can add nodes to the DOM, remove nodes to the DOM, and access other APIs, for example, about the geolocation, about the cookie store that we're going to discuss in a moment, etc. Let me discuss now one important aspect about HTTP, which is state management. We said that HTTP is a stateless protocol, which means that the server has no memory. But you are familiar with applications which actually have memory. If you use streaming platforms such as Netflix, Prime Video, whatever you like to watch, you know that these systems keep an history of what you watched in the past and might implement a recommender system to recommend you movies that you probably like. If the server had no memory, it would be impossible to implement something like that. So in this scenario, we can see the client requesting a movie with the following ID, and the server has enough information to reply and provide the HTML of the streaming page. However, when the client later navigates back the catalog, if the server has no memory, the server has no track that the user previously asked for the movie with ID 54321. So in this case, the server will be unable to implement the recommender system. So how can we deal with that? Because as a matter of fact, we want to build a stateful application. And the answer is cookies. So the key idea of the HTTP protocol is that the server doesn't keep track of any state. State information is managed by the client. In particular, HTTP clients, such as browsers, have support for cookies. What is a cookie? It's very simple. It's a misunderstood concept for many people. They have a bad name, but actually the concept of cookie is quite neutral, because a cookie is just a piece of data, which follows the key value format. So a cookie has a name, which is the key, and a value, and you can put whatever you like into the value. So for example, here we have a cookie, which is called lang, and as value en, which includes that the user of the system speaks the English language. So we want to interact with the server using the English language. As I said, they're stored in the client, but they're set by the server. So the server creates the cookie and asks to the client to keep track of that. So the way we set the cookie is by means of HTTP responses. So we use the set cookie header to pass the cookie to the client. And the cool thing is that the next request coming from the client will automatically attach the cookie. So the client populates further HTTP requests by using the cookie header, which attaches all the cookies which were previously created by the server. So what is interesting is that state is saved by the client, but it is basically reattached to all the next requests, so that the server can always extract the cookie from the request and reconstruct the state information. Cookies are opaque. So if you look into the cookie jar, you find a lot of information, but you don't necessarily understand the content of the cookie. So this is your favorite streaming platform. You request a movie, you put the ID of the movie into the request. The server sends you back a cookie, for example, the cookie scene, which contains the list of the movies that you watched. It's not the only available implementation. Cookies give you a lot of freedom, and we're going to discuss about all the bugs which come out of this freedom. But in this case, I will provide you with a list of the scene movies using the set cookie header, and the next request automatically attaches the cookie using the cookie header. And now the server, just by processing this request with no memory, has enough context to access all the movies that you watched back then and provide, for example, a personalized user experience. This is also what normally happens when you authenticate with a website. So you send the password, and after the password change, you set a cookie, and the cookie identifies you back in subsequent exchanges. But we're going to discuss this in a few classes. Let me just introduce this topic. We're going to discuss about this more on Friday. As I said, cookies are attached automatically. So if you put a cookie into the browser, the cookie is set to all the requests toward the same fully qualified domain of the server which set them. So if we have www.example.com, which sets a cookie, only requests to www.example.com will attach the cookie. However, you can control somehow the scope of the cookie. We have a path attribute of the cookie. So the cookie can have an additional keyword, which is path, which tells to which path the cookie must be attached. And you also have a domain attribute, which allows sharing with subdomains of the domain which set the cookie. You can see this information also from your browser. Let me show that. If you go here in the application tab, you will see that these cookies have a domain attribute. For example, this cookie here, which I'm highlighting, is a cookie which is shared with any subdomain of Gazetta.it. You see the domain attribute is set to .gazetta.it, means every subdomain of Gazetta.it gets this cookie. And as you can see, the path attribute is set to /, meaning that all the paths under Gazetta.it are going to get the cookie. As you can see, the path attribute is hardly customized. ignore for now cookies that you find in Gazeta, but have a domain which is different from Gazeta.it. We're going to discuss about this when we discuss more in detail the same origin policy and web tracking, which is one of the topics that we're going to cover. Okay, connection failed, lecture is done. Bye.